Joining Chemistry 30 in progress. We're continuing on with intermolecular forces, and we're looking more at these structures, especially the 3D structures, and we're going to see some models. And we actually have names for the molecular shapes, 3D structures. So, now the first one, CO2. I'm giving you the name linear, and I don't know if you recall what CO2 is like. I'll demonstrate it right here, and it doesn't show up on video, and then we'll jot it down. I'll start the video again. In the classroom, I'm holding up a model of CO2 with the double bonds, right? Does it make sense, the name linear? Right, it's a line. And the 3D structure is also a possible structure. I'm going to just draw it. See? You've got to make it look like it's in line. And then you've got to put the electron pairs there. I want you to put that on for each other. And make your pairs group together. Don't space them out either. Now, I use CO2 as an example. It has three things. It's a line. I'm going to erase this example, but just mention this. Anytime you have something that's just two, you're guaranteed it's a line. The only way to join two things is to like H, CL. That's linear. But I mean, that requires no thought. That's the only way to do it. Like here's something a little more common. Now, why is it like that? I'm going to hold the model up and refer to the diagram, but it doesn't show up on video. Because these electrons that are represented by the springs, those are the electrons in the double bond are natives, right? You know about light charges, repel or attract. Light charges, repel. So, if I think, and this isn't going to show up on the video at all, I'll represent me as the carbon in the middle, and then this hand, this is the oxygen here, and this is the oxygen. Now, I want this negative arm, this double bond here and this double bond here, to be as far apart as possible. Obviously, too close together. They come together and whoop, then they go back, whoop, too close together, right? This is as far apart as possible, 180 degrees, right, in a three-dimensional structure. That's as far apart. I'll jot down that to 180. I think you all understand 180 is a strict line as far as an angle, right? Yeah. But this one here, I remember I said almost everything wants to add up to 8 electrons in one. This is an exception. High school, and I do other exceptions. BF3, a boron. Single, single, single. And for reasons we're not getting into here, I'm just going to say this is the way it is. So only wants 3 bonds. It does not want to get a total of 8. Now, I drew it the Lewis structure way where it's 4 sides I'm picking. But in reality, these bonds, you have 3 things and you're trying to get them as far apart as possible. What angle do you really want? Like, how would I space them up? A triangle is not 90, because these are 90. Right? So if I had bond, 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 you know that this one here is going to push on this, and it's going to go wider. So we're going to end up with the triangle idea. Yeah, right? Now, whether you put it upside down or right side up for a letter Y, it's up to you. Now, the modeling kit that we have doesn't represent it. But it's the same logic here. BF3. S dot. they represent the unpaired electron pairs. Unpaired, I said that's wrong. Non-bonding electron pairs. Now, with that, it's 120 degrees. And I'm going to just do something that won't show up on it. But these angles are 120. And it's because of the repulsion. Now I'm going to go back up to the title. Valence shell electron pair repulsion, the second. The whole idea of this geometry is that negative electrons repel each other, trying to get as far as possible. Bonds, covalent bonds, are made up of negative ones. Now, that's a flat triangle. So, when I say it's a triangle, I think you got it from the root of the trigonal plane. Maybe not. You can imagine. Okay, a flat plane, right? Triangle, trigonal. So, what's going to happen is that you're going to have questions. I would say, which geometry is this? And I'll have the whole list of all these linear, trigonal, planar, and tetrahedral. Okay. Trigonal in the middle later on. So then the next shape, tetrahedral. Now I'm going to draw it, but you don't want this. This is CH4. This is the Lewis diagram. This is not how it shows up. Because they're definitely not as far apart as possible. This one requires a little more imagination. How could you get four things as far apart as possible? Well, if they're 90 degrees, remember it's three-dimensional space. So you might kind of push them up or something like this. It doesn't show up on a flat diagram. So if I got four things, you see when I hold this up, these are all equally far apart from each other. As far apart as four things can be around the center. We know how to draw this if we've drawn this shape before. So we're going to use the convention used in chemistry to draw this. So, and I've even mentioned the angle before, 109.5. So I'm going to go with this. Always make sure this does not look like 90 degrees. Now the other one, is you squish them in. That means it's coming out of the board, out of the plane. Okay. This one going behind the board, behind. You should look at that diagram and imagine it's this, right? It's a, I think of it as a tripod sitting down with a little top to it, right? I've had that before. I don't know. Some years I have. Andrew was in my grade 9 class for a little bit, right? Who else was? Somebody else? Gerline was, weren't you? No, you weren't. Right? No. Anyway, well, I can assure you, like, I do test it like that. I forgot. I'll have the video. Tetrahedral. It's a four-sided kind of thing. Anybody play it's like game? With the weird dice and stuff. Dungeons and Dragons. Is that what it's called? Yeah. You ever see a four-sided die? You know what those die are called? Tetrahedron. So if you kind of like, these are the corners of that four-sided die. So you have a flat side here. That's what the shape is. It's not a very common, but it's not a shape name that you learn in grade 3. So it's not so common. Talking, and I misplaced my pen. Where's it gone? Lord love it, duck. There we go. Yeah. Sorry about that outrage. Now, if I go to pyramidal, and I'm going to compare it to this tetrahedral shape because all it is three things attached. Boom! Three. Don't argue with me. Okay. Does this look like a triangle-based pyramid? Hold the power of the pyramid, right? Good. You just took the top off of that tetrahedral. Hey, exactly where this is happening. H. What is it? Okay. Here's your triangle-based pyramid, trigonal pyramid. The names make sense. I'm going to give you the list of the names you're going to label or draw as needed. You need the lone pair of electrons here because they are repelling them down. Without those electrons, I'll do this with the spring. I know it doesn't show up on the video, but whatever. Hope you're having a great time with band trip. Maybe while you're watching the video. Big shout out to all the sousaphone players. Most underrated instrument. Where are we going? Oh, yeah. We're going to burn down the city. Okay. Right now, I took this out so we can move these things. Without this, it's far apart without those pair of electrons. They'd be a flat pyramid, trigonal plane, right? The minute I take these, and imagine this like a magnet repellent, negative, push it on, and it pushes those ones down. Does that make sense why it's this shape? Still got four things. That's why I want the electron pairs put on there, because it explains why they're the shape they are. Okay? So it's just a variation of tetrahedral, taking off one of the arms, one of the bones. Okay. Now, bent is just a tetrahedral shape of water, is the example of bent. But let's put water in a model kit, and we always use the sticks to represent the electrons that are paired, or aren't bonded to pairs. Doesn't this just look like my tetrahedral shape again? But the electron pairs are occupied. Now, to make it easier to draw, don't do 90 degrees, because that's not what we're talking about. We're going to draw this part of the tetrahedral shape. So, I'm going to draw this part of the tetrahedral shape, and put the electrons here, and this occupy these ones. Okay? Those are video lab. So, O, central atom. I'm showing, the important thing is if you draw a water molecule, I want you to draw it so that the bond does not look like it's 90 degrees. Now, you have to draw it like that. No, I'm just drawing it so that you can compare it. This is what I was just going to say. I'm drawing it so that you can see how tetrahedral shape is the basis of the other shapes. So, you're asking, is it okay if I did water like this? Oh, as long as it does not look like 90 degrees, close to 90 degrees. I want the angle to be, it's actually not perfectly 109.5 in this case. Did I put that angle down on that other one? You know what? Quickly jot this down and then the bell's going to ring. Oh, 109.5. Sounds like a radio station. Degrees. Okay? Then we're done. Over and out. Over. Have a good one, Dan Trippers.